This video is going to talk about how to estimate the minimum of a cost function. So here's the situation we're in. We're doing some nonlinear least squares. So in the previous video, we talked about a particular problem where we had this nonlinear function, and we have some data that goes with it. And we could write out a cost function. And so the cost function involves making the differences between the observed values and our function as small as possible. More precisely, the square distances between those two as small as possible. Okay, so how do we minimize this function? Now, if this were linear regression, there'd be a simple closed form equation that would give us the answer. But when you have a nonlinear equation like this, you can't just write out the solution. You can't just find the solution in what we're going to call closed form, where that's just a simple equation. Instead, we need some numerical methods that will allow us to take steps towards finding that. Okay, so the first thing I want to note, back on this is that if we want to minimize some function, what that really means is we want to find the point where this curve has a slope of 0. Okay, that's what I just said is a really profound statement. It might be easier to see through an example, and we're going to use this example in a few minutes. But this picture on page 14 here is a picture of one of these cost functions. Okay, so these are different values of the parameter. And so for some values of the parameter, our cost function is higher than for other values. And what we're trying to do in this problem is find the point where this cost function, so the sum of squared errors, is as small as possible. Okay, so the point where this cost function is as small as possible gives us a value of the parameter that's called the least squares estimate, because this value is the one that has the smallest sums of squares. So what I said a minute ago, that profound thing I told you was the way we can find the bottom of this is to find the point where the slope of this curve is completely flat. All right, so how do we find the slope of this curve? And the answer is there's a technique in calculus called taking the derivative. And so the first derivative of this function describes the slope. So I happen to have the first derivative over here. There's a number of ways to write this derivative. One is to write it as dj db. So dj over db, that's just for a small infinitesimal change in the function divided by a small infinitesimal change in the parameter. So that's the slope. All right. So if you let those things be very small, so let's just take a quick look at these two figures. So what we have on this left-hand side. So notice the x-axes are the same, or the b-axes in this case are the same, and what we see is that this curve has a negative slope. So if we were to, the slope is kind of pointing up and to the left, which means that the slope is negative. So if we look up on the right, what you'll see is that this first derivative is negative at that point because this curve is pointing off to the, off to the left. All right, I don't know if I said right a second ago. I think I gestured right. I may have spoken wrong. Okay, now at the point, this is a little bit more than 0.2, where this cost function is completely flat, you're going to notice the slope is exactly 0. Now what happens after this is that the slope becomes positive, and that's reflected by the fact that this first derivative is positive. Okay, so what's really important to understand is that if you want to find the minimum value of a cost function, that corresponds to the point where the first derivative function crosses the x-axis. Okay, so that's called a root. So where does this first derivative function cross the x-axis? And if we can find that, then we can find where the bottom of this is. All right, so that is the biggest idea that we have right here. So we're going to go find a derivative. Now this is for a multivariate function. This is this fancy version of a d, if you will. But this is basically still the derivative. We just want to find where this thing equals 0. So there's a lot of ways to do this. One way that I'm going to talk about right now is called Newton's method. We're going to find that Newton's method is going to have a problem. So the problem is that we need to compute something called the second derivative, and when we have a lot of parameters, the second derivative involves a lot of pieces and a lot of computation, and that's not going to be practical in a lot of cases. But we're going to start with Newton's method because it's a very nice place to begin, and it's of historically great importance. And a lot of methods like logistic regression use Newton's method in software. So you should have heard of it. All right, so to understand Newton's method, let's say that I have some function h that I want to find a root of. Okay, so what you should be thinking here, what h is going to correspond to is the first derivative. Okay, so remember I said we want to find where the first derivative here is a root. It's crossing the axis. But for now, I'm going to introduce a new symbol for it. We're going to call it function h. All right. To understand what Newton's method does, normally I draw this on the board. I've made something in PowerPoint. So what I've sketched out is, let's say that this is some function h. And what I ultimately want to do is find where this function h crosses my x-axis. All right, fine. Well, let's say I have some x value, and we're going to call this a starting value in a minute, but it'll be labeled x naught. So here is x naught, and if we go up to the function, the height here is really just our function h evaluated at that point. Okay, cool. We can find the slope of this h function at that point. Now, the name of this this slope, it can have different names. One name that we're going to use is h prime at x naught. All right, so this is just how steep is this curve at this point. That's the way to think about that. That's what the slope is. So this is the first derivative of the h function. All right, well, let's say I have another x. So here is another x. And if we kind of go up to the function, this is the value of the function h at this point x. All right. Now, what I want you to notice is that this point on the curve is really close to the point on this tangent line. All right. So in particular, if you think about the math, this point on the function h at x is approximately the same thing as the point on the line. Well, what is the point on the line? So let's start out at h at x naught, and then notice my run, or the change in the x direction called the run, is x minus x naught. So I'm going this far to the right, so x minus x naught. And how far do I have to go up? Well, I go up the slope times that. All right, so if you think about the slope as rise over run, my run is this, if I take the x minus x naught times the slope, I get the rise. So the point on the line, h at x naught plus, this is, the slope times the run gives me the rise. And so I've approximated this function with this linear equation. And now I've exaggerated things on this picture. In real life, you're kind of hoping you're really close to x naught, and you could see where this first derivative function is very similar to this function h as I'm really close to x naught. When I get further from x naught, then it's not as close. But okay, so this is a really key formula that I hope you now understand, the geometric interpretation of. So, in order to find a root, what that really means is h at x has to be 0. So this point here is where h at x is 0. So what I want to do is find the x that goes with that point. All right, so if I just put a 0 here and solve, I end up with what's called the Newton update formula. Okay, so my next x, x1, is just going to be wherever I started minus this update procedure. All right, so to illustrate this, I'm going to take us to the Wikipedia page, and there's actually a really nice example of Newton's method right here. So I'm gonna make it bigger, and so here we start out. We find the tangent. We solve for the root. All right. Now we find another tangent. We go over here. We find another tangent, and we got another tangent. And so what you should see is that we're getting closer and closer to the root. That is the whole idea of Newton's method. So you want to watch this little video loop multiple times to really understand this. Okay, so I'm going to close that. That's the whole idea of Newton's method. So what I've done here is put together a very small example to illustrate this. So let's say I want to do a nonlinear least squares estimation on this function, e to the minus beta x. This is a very easy problem because there's only one parameter involved. In a few minutes we're going to take this to higher dimensions, but we're going to start in one dimension. I call this the tiny example because we also, in addition to having one parameter, we only have 3 observations of data. So what I'd like to do is first estimate this with the NLS function in R, which I think is an excellent function it makes your life very easy. But then we're going to implement this by hand, if you will, using Newton's method. All right, so remember I said it's really important to find starting values in the previous video. So I'm going to try to linearize this and find a good starting value. So if I take the log of both sides, log of y is just minus beta x. So I can do least squares right here. And I have a pretty good starting value, minus 0.2000 something or other, 28. All right. Now, we're going to go into NLS. And remember I told you last time NLS looks a whole lot like LM. You give it a formula. And so this formula, y is e to the minus b times x. You give it your data frame. So tiny is my data frame up here, which I defined in one line. And then the only other thing is you need to give it some starting values. So what are the starting values? Well, just minus this coefficient that I estimated up here. All right. If we want to go do this live, I can go over to R and show you this live. So let's go read in the data. We found our starting values. We estimate the function. Let's go plot it. And I'm going to go superimpose it with some predicted values. And you can see the fit is very, very good. All right. So, we've done it, and the correct answer is pretty close to our starting value. So 0.2034 something or other versus 0.20028. Now, let's go implement this with Newton's method. So I think it's really important for you to have an understanding of you're probably wondering, why do I make you do this by hand when you have this NLS function? I think you learn a lot, and when we get to neural networks, you will not always have these canned procedures, and you might have to write your own. So it's just good to understand what these things are doing. So what I've done, I've started out by writing a function in R that is the objective function. So there's my objective function, the least squares objective function. So think of this as y minus y hat squared, y minus y hat squared, y minus y across the three observations. I have handwritten out the first derivative function. So the first derivative function we can call j prime. That's what, remember I said just stick a prime by it and you get the derivative. Or we could equivalently call it dj/db. And if you haven't had calculus, don't worry. In calculus, you would learn how to take the derivative of it, and this is it. All right. So I've graphed the function here, and we've already gone over those plots. So remember, with Newton's method, it all comes down to this update formula that we derived on the slides that I showed you. So the next value of my parameter estimate is just the previous value, and we're going to adjust that by the ratio of h at this divided by h prime. Now in this case, it's really important to note, is my h function is the first derivative function. The first derivative of h is the second derivative. I know that's kind of confusing, but it is, because we're studying the root of the first derivative function, not the root of the cost function. The cost function may never even cross zero. All right, so here's the second derivative. In calculus, you'd learn how to do that. If you don't know how to do that, don't worry about it. Here is the R implementation of that thing I derived by hand. Now there's one thing that I strongly recommend, which is to check your work. I inevitably screw up the derivative calculation. I admit that the algebra gets messy on this, and I can't help but to make a mistake, or maybe I type wrong. So the first thing that I always do is with something called the finite difference method. So I'm just going to evaluate this h prime function, or the second derivative of the cost function, at 0.2, and you'll see the value is 8.6. So if you think about what a derivative is, it's the change in y over the change in x. So I'm going to take the first derivative function plus a small value, so 10 to the minus 6th, minus the first derivative at 0.2. So that's like the rise for a tiny change in x, and divide that by the tiny change in x. So this is the run. And what you'll see is these two numbers are pretty close to each other. They're not exact, because this isn't, this isn't 0. If we were to let this go to 0, these two numbers would get right on top of each other. All right. So let's talk about the Newton function that implements this. So the Newton function, we're just going to set the iteration counter. We're going to set some things up. Then I'm going to have this while loop. So while the difference between my objective function values is greater than some small tolerance value that I can set, we're going to do this update procedure. So this is that Newton update formula that I showed you at the top and that we derived on the previous slide. And so we're just going to keep doing that. And so what you're going to see is that we start out at 0.200, and after about 4 iterations, we are right at where NLS landed So 0.203449, and that's pretty close to what we found here. So that's what's going on in the background when you use NLS. All right, in my next video, we're going to talk about the gradient descent method and the secant method, but I think we'll make a separate video for that.